Hello viewers, in my last lecture I discussed about solid liquid equilibrium, the phase diagrams and systems that show eutectic mixture formation, and also the systems in which the components have a tendency to react to form compounds. And we have seen two types of behavior there: compounds showing congruent melting point and compounds showing incongruent melting point. We will continue our discussion about these systems in today's lecture, and we start with the introduction, solid liquid systems, and then discuss about some examples of such systems, and mainly the examples that we have taken up for discussion is bismuth cadmium system, lead silver system. These two systems we will be discussing in detail. The other examples will be mentioned, but then there is one class of compound or system which are very useful and very interesting, are salt water systems, in which the salts form hydrates. We start with potassium iodide water system. It pertains to a simple eutectic system. The second system that we take for discussion is ferric chloride water system, where there is a compound formation, a very interesting system in the sense that ferric chloride is able to form a series of hydrates. And then we take the common example of salt water system, in which there is compound formation, but this compound is not stable. It undergoes a peritectic reaction. That means it exhibits incongruent melting point, and these systems can be used as freezing mixtures, and we see some examples of freezing mixtures, and then I will summarize what we have seen today. Let me take up the example of simple eutectic system, the bismuth cadmium system, lead silver system, zinc aluminum system, copper silver system, tin zinc system. We start with bismuth cadmium system. The phase diagram of this system is given here. Looks very familiar to you because you have seen the general behavior of simple eutectic systems. You can recognize the curves. A, B are the melting points of the two components that are there. Their respective melting points are given, and then by the addition of the other component, the melting points go on decreasing. If you take A, that is bismuth, its melting point decreases after the addition of cadmium into it, resulting in the decreasing freezing point along the line AC. Similarly, to cadmium, if we add bismuth, the melting point decreases. Ultimately, the two lines meet at point C, and we have seen that the point at which the composition is such that it exhibits the lowest melting point is called the eutectic composition, and the temperature at which this is shown is called the eutectic temperature. And you can clearly see that in this system, eutectic temperature is much lower than the melting points of the two metals from which it is formed. Experience tells us that the curve AC is called the solubility curve of bismuth, and similarly curve BC is called the solubility curve of cadmium, and the values of degrees of freedom are shown. F prime is equal to 2 is a bivariant system, and where we have two phases in equilibrium on either side here, F prime becomes 1 univariant system, and the eutectic point is the place where we have the degrees of freedom is equal to 0, indicating that that is our invariant point. Just to give a taste of what you studied last time in a general system, let us start with a mixture of the two metals here corresponding to point A and cool it, and we know that number of degrees of freedom at this point is F is equal to 2. Therefore, cooling is allowed. we can follow the path shown by the arrow here, and the cooling takes place till we reach the point B, at which some solid makes its appearance. In this case, we can recognize that the solid that is likely to separate because of the overall composition is cadmium. We lose 1 degree of freedom, and cooling can take place further with more cadmium getting separated from the melt, and this can happen till we reach the point C on the curve here, the horizontal line that we have drawn, where the other curve intersects, indicating that the system becomes a 3-phase system. We had cadmium and the melt. Now bismuth also makes its appearance. Because of that, we lose the degree of freedom that we had. Ultimately, we get the value for degrees of freedom 0. System becomes invariant. There is a temperature halt till the melt completely disappears. And further cooling is possible when we have only solids present in the system. So it is possible for us to explain the phase diagrams based on the general system that we had seen last time. Another interesting system is lead-silver system. This also belongs to simple eutectic system, and you can see the diagram here. Very similar diagram. You have one end you have 100% silver, the other end you have 100% lead, and you can see the eutectic point C here. The temperature corresponding to eutectic point is 303 degrees, which is lower than the respective melting points of the two participating elements. AC is the melting point of silver as it changes with the addition of lead, and similarly BC tells us how melting point of lead decreases with the addition of silver in it. This phase diagram has been used in an interesting extraction process. We know that argentiferous lead contains very small quantity of silver. It is about 0.1 mass percent. Extraction is difficult, and also it is not economical. In this process, argentiferous lead is heated and cooled, during which pure lead gets crystallized, and lead that has separated can be taken up continuously. Melt that is present as lead gets separated, that becomes richer in silver. And if you look at the composition, ultimately that reaches the eutectic point, where the composition has become much richer in silver. That is about 2.5 mass percent of silver, which can then be subjected to other procedures and processes for recovery of silver. As I told you, under solid liquid equilibria, there is a system or group of systems in which we have salt and water present in equilibrium, and such systems are very useful as we will see it. One characteristic of this system is that the phase diagram looks incomplete. Why? This is because the melting point of salts are generally high, and these temperatures are much more than the critical temperature of water. Therefore, liquid water has no existence above its critical temperature, and that is the reason we cannot trace the phase diagrams to the extreme right, where we have almost 100% salt. However, in some systems the studies have been carried out at high pressure, and it is possible to see the full phase diagrams. Next interesting system is the saltwater system, in which we have some information because we are familiar with solubility curves of salts. We also know about solubility limit, and we also know about effect of temperature. Some of these experiments we might have carried out, or you might have carried out in your labs. What common observation you might have made? Solubility of salts generally increases with increasing temperature. Of course, there are exceptions. You may have some salts where solubility may decrease with increasing temperature. When the salt is added to water, it first dissolves, giving a clear solution, a homogeneous solution, and when you add excess of salt, go on adding with stirring, it starts separating out, no more dissolves, indicating that the solubility limit is reached, it forms a two-phase system. Solution, that is saturated, in equilibrium with solid salt. This is nothing but a part of the phase diagram. One important observation you might have made even at home, that dissolution of salt is accompanied by evolution of or absorption of heat. It may become cooler, or in some cases it may become hotter. Let us first look at the potassium iodide water system. The phase diagram of potassium iodide water system is here. It looks like the eutectic systems that you have studied earlier, but only difference that you recognize, as I told you, is that the phase diagram looks incomplete because the temperature at which the salt melts is substantially higher, where liquid water cannot exist, and therefore we terminate this line abruptly at point B. As I told you, A is the freezing point of water, that is 0 degree centigrade, and as you add potassium iodide to it, the freezing point decreases and reaches the point C, and this gives us the solubility curve of potassium iodide. The two curves intersect at point C, and experience tells us that when you have the two curves intersecting, there will be three phases: ice, salt and the solution. The system becomes invariant, that is F prime becomes equal to 0. The point C is also called the cryohydric point because we are talking about the salt that is present in equilibrium with ice. The other interesting system is ferric chloride water system. Interesting because ferric chloride and water form a series of salt hydrates, and all these salt hydrates have sharp melting points. You recall compound formation, where the compounds exhibit sharp melting points. They are called congruently melting solids, and these are the salt hydrates. You can look at the formula of the hydrates. We have written double formula because we want to avoid the fractional number of water molecules with each of these hydrates. We have made it 12. It should be 6 FeCl36 H2O. Instead of that, we are writing the double formula so that we have whole numbers 12, 7, 5 and 4 for the water molecules. The phase diagram looks very interesting with so many humps, and each hump corresponds to a salt hydrate. This is corresponding to dodecahydrate, this is heptahydrate, the pentahydrate, and this is with 4 water molecules. We can say that whenever a hump appears in a phase diagram, we can conclude that the two components form a compound having a congruent melting point. Interesting observation that can be made here. You can see here the dotted line. That means we are talking about the metastable equilibria. It is possible to trace the solubility curve of the dodecahydrate to a much lower temperature than when the heptahydrate appears, and such one-way transitions that are possible are called metastable transitions. This adds to complexity for the interpretation. Some unusual observations have been made in this ferric chloride water system. If you start with point A here, this is the region in which we have ferric chloride is dissolved. That means you have an unsaturated solution. It's a bivariant system, and if you move along this line, horizontal line that we have drawn here, which is an isotherm, it cuts the curve corresponding to the solubility of ferric chloride dodecahydrate at B, and this curve continues on the other side after the maximum. It cuts again at point C, and the whole hump corresponds to the solubility curve of the dodecahydrate. At a given temperature, you have point B and point C, both correspond to the solubility of the dodecahydrate. The question then arises, for a given salt, how can there be two solubilities at the same temperature? Now, what we try to find out is there something wrong? But if you carefully look at, we can see that the solubility corresponding to B, the composition of the solution with which it is in equilibrium is much different from the composition of the solution that you have corresponding to point C. Therefore, these are the two solubilities of the same substance at the same temperature, but in two different solutions where they differ in their compositions. Such solubilities are called retroflex solubilities. This picture gives you a clearer idea. You can go from here to here, salt appears. Which is the salt? You have ferric chloride heptahydrate, and we move along the line, again ferric chloride heptahydrate, and when you cross this at constant temperature, you will see the region, you are re-entering the region in which you have homogeneity, only you have a solution. So, you have the existence for the salt from B to C, and as I told you, we are talking about retroflex solubility in this case. Sodium chloride water system. This is a system in which we have a ferritectic reaction. The components have a tendency to form a compound, and this compound is not stable and cannot be heated to its own melting point. Before reaching that point, it decomposes to give another solid and a melt where there is a difference in composition. And in this case, sodium chloride forms a salt hydrate, NaCl2H2O. It is a dihydrate. It decomposes at a temperature slightly higher than the freezing point of water at 0.15 degree centigrade to give anhydrous sodium chloride and water. This is nothing but a peritectic reaction, and we can see here an equilibrium between the dihydrate and the anhydrous salt plus solution. Three phases are there, and it tells us that the number of degrees of freedom corresponding to that should be 0. So, here is the phase diagram of sodium chloride water system. We can easily recognize that it is a system in which there is a peritectic reaction. We have the line here which gives us the freezing point of ice. As the amount of salt is increased, freezing point decreases. This goes almost vertical. With the increase in temperature, the solubility of the dihydrate does not increase much. Even beyond that, solubility of sodium chloride also does not increase much with the temperature. Regions can be easily recognized. This is the bivariate region in which we have salt solution or the brine, a homogeneous system, and here you have a univariant system in which we have ice crystals that have been formed in equilibrium with the solution. On this side you will see a vertical line almost. This corresponds to the solubility curve of sodium chloride dihydrate, and further up you have the solubility curve of sodium chloride anhydrous, indicating that there is hardly any effect of temperature on the solubility of the dihydrate as well as sodium chloride. The horizontal line where we have shown an equilibrium between the dihydrate, anhydrous sodium chloride, and the solution corresponds to the peritectic reaction, and the point here is called the peritectic point, at which the number of degrees of freedom is 0, because there are 3 phases in equilibrium. It is very clear that above this horizontal line, that means above peritectic point, the dihydrate cannot exist. Therefore, we have a system in which we have salt solution for which the number of degrees of freedom is 1, because the solid sodium chloride is also in equilibrium with solution. If you look at the diagram, and if we start with point A here, at which we have F prime is equal to 2, and if we try to cool this, the system will not resist. The temperature decreases, and when we reach the point B on the curve, ice starts separating out. Further cooling is allowed because we still have 1 degree of freedom. More ice separates out. and we reach the point C, the solution composition starts drifting towards C, and we recognize this as the eutectic point, or in this case the cryohydric point, at which there are 3 phases in equilibrium. The ice that has separated as we cooled the system from B to C, the solution that is there in equilibrium whose composition has just reached C, and at this point the solid dihydrate NaCl2H2O also makes its appearance, giving rise to a 3-phase system. The degrees of freedom is lost, that there is a temperature halt, and when complete system has frozen, when no more solution is present, the temperature decreases, leaving out the sodium chloride, dihydrate and ice. It is the eutectic composition you have here, and also you may have primary crystals of ice on this side of the eutectic system, or you may have primary crystals of sodium chloride dihydrate on this system. We can think of an application for this and use this diagram to explain. So, if you have a salt solution, if we cool it, immediately what comes to our mind is salt will start depositing, it will crystallize out, because with the decrease in temperature, the solubility of salt decreases. But in this case, if the overall composition is to the left of C, as you cool it, what crystallizes out is pure ice, and it continues to give us pure ice till we reach the point C. We can get pure ice. You can think of, if you have an iceberg and ask a question, is it pure water that has frozen? Most likely, because if the salt composition is less than this point, the iceberg is formed by pure ice and there is no salt, and in fact it can be a source of potable water. Now, it is also found that the temperature corresponding to this is about minus 21 degrees centigrade. We have a practical application for this system. If you recall, and many of you might have tried to prepare ice cream at home, what you do? You take crushed ice and put salt layer after layer to create a low temperature bath in which you can get the ice cream. Only ice will give you only 0 degrees centigrade, not lower than that, but the mixture gives you temperatures much lower. We are talking about freezing mixture. But the question that arises is, why temperature decreases when crushed ice is mixed with the powdered salt? Or another question can be asked, why temperature becomes constant at minus 21 degrees centigrade? Both these questions can be answered. See, we know that when we add salt to crushed ice, the salt will dissolve in the small amount of water that is formed on the surface of ice. The amount of water is so low that the solution formed is highly concentrated. In order to dilute that solution, more ice will melt, more water is formed, so that more salt can dissolve. That means we have melting of ice, dissolution of salt, melting of ice, dissolution of salt. This process continues. Why temperature decreases? Dissolution of salt and melting of ice are both endothermic reactions. As there are 3 phases, namely the ice, salt, which are both solids, and the solution in equilibrium, number of degrees of freedom is 0. This 3-phase system is stable only corresponding to the temperature minus 21 degrees centigrade, which is the eutectic temperature or the cryohydric point in this case. At any higher temperature, when the salt has dissolved, the solution is formed, you have a 3-phase system. According to phase rule, the system is not stable. Therefore, this process of melting of ice, dissolution continues, and ultimately when the temperature reaches minus 21 degrees centigrade, the system becomes stable. There is no problem, number of degrees of freedom is 0, you have a 3-phase system which can exist, which can be say stable system. Therefore, the temperature becomes minus 21 degrees centigrade and remains there. This temperature is maintained as long as you have salt and ice, if one of them is consumed, either entire salt has dissolved or the ice has melted, then the situation changes, the temperature starts rising. But as long as three phases coexist, the temperature will be maintained at minus 21 degrees centigrade. Now, we can think of another application which I mentioned in the beginning of my lecture. What is that? If there is a heavy snowfall, if you sprinkle salt over the snow covered road, there is a possibility that salt will make the snow to slowly melt away and the road gets cleared. And there are better salts that are used, maybe more expensive, but if the temperature is above minus 21 degrees centigrade, sodium chloride can be sprinkled in order to remove snow covered roads and make it clear. Not only sodium chloride, we can also use other salts, as you can see here: calcium chloride, potassium iodide, sodium iodide. In fact, there are other systems also which can be used to get low temperatures. Ice in combination with organic liquids like alcohol, ethylene glycol, glycerine, as well as we can think of a mixture of acetone and dry ice. What is dry ice? Dry ice is solid carbon dioxide, which gives us much lower temperatures. Let me summarize. We started with solid liquid systems in the earlier lectures and we continued with it with some examples that we have taken up today: bismuth cadmium system, lead silver system, and we took up salt water system where the salt hydrates are formed. Three systems were discussed: potassium iodide water, ferric chloride water, sodium chloride water systems. Each one is different, simple eutectic, compound formation with congruent melting point, and then compound with incongruent melting point. And we ended the lecture with some freezing mixtures to produce low temperatures that we use at home and in the lab. In my next lecture, I will take up systems in which the two components show miscibility in the solid state. That means solid solution formation. Thank you.